Okay, so Section 1 covered the types of units in gas laws and their conversions. Section 2 covered what's an ideal gas and some of the assumptions we have to make about gases. Section 3 is going to actually get into the mathematical relationships, and this is one of my favorite units and one of my favorite sections of the year here. We are going to learn 4 laws today, and there will be some more, but these were the first 4 gas laws discovered. The first one is called Boyle's Law. It's named after Robert Boyle, who was an Irish scientist living in the 1600s. He's going to discover a relationship between pressure and volume. And he discovers that that relationship is inversely proportional. Now, there's 2 types of relationships. There's inversely proportional, and there's directly proportional, which we'll see here in a few minutes. Okay, those are the 2 types of relationships. Inversely proportional means as one variable goes up, the other variable would go down. Whatever one of them does, the other variable does the opposite thing. Directly proportional means if one of them goes up, the other one would also go up. Or if one goes down, the other one also goes down. So what that means here is that Boyle discovers that if, say, pressure goes up, that means that volume must go down. Or if pressure goes down, then volume must go up. He discovers their relationship is inversely proportional. Okay? He has nothing here about temperature, so his law is assuming constant temperature, which we'll talk about here in a moment. But he discovers this relationship between pressure and volume is inversely proportional. His law states this. We'll see it in mathematical form here in just a moment. The volume of a fixed amount of gas held at a constant temperature varies inversely with the pressure. Okay, so fixed amount of gas, that means constant moles. Means we can't change the amount of gas. We have constant moles held at a constant temperature, okay? So constant T. So we can't change the temperature. But pressure and volume vary inversely, meaning whatever one of them does, the other variable does the opposite thing, okay? His law does not require specific units. This is important, but it have to be consistent. So let's say, your pressure is in atmospheres. That means all the pressures in the problem need to be in atmospheres. Or if the volume is in milliliters, all the volumes need to be in milliliters. So this is one of the few laws that doesn't have a specified unit that you must use, but you do have to be consistent in the ones you pick. Okay, so here's his law in mathematical form. It looks like this. P1 V1 equals P2 V2. Okay, it means initial pressure times initial volume equals final pressure times final volume. It results in a downward curve. You should know the shape. You should know the shape of an inversely proportional graph. It results in a downward curve, and that should make sense, right? As my x variable is getting bigger, my y variable is getting smaller. Whatever is happening to one variable, okay, the opposite is happening to the other variable, since this is inversely proportional. Okay, and you can kind of see what's happening here. If we start at 1 atmosphere in 10 liters, okay, if we double the pressure, the volume got cut in half. And if we double the pressure again to 4, the volume got cut in half again. So you can kind of see how this relationship works, right? It's got a downward sloping curve. So the equation again, P1 V1 equals P2 V2. Make sure you've got that down. That's Boyle's law, the first one. Okay, let's try this sample problem together. A diver blows a 0.75 liter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atmospheres to 1.03 atmospheres. What will be the volume of air in the bubble at the surface? What I like to do with these problems is to label what the numbers given are and then try to figure out which equation we're going to use. Since this doesn't say, use Boyle's law to solve it, we try to figure out, which one are we going to use because I have 3 of the 4 pieces of it. And you'll see with the other laws here that this will be helpful. So let's go ahead and label things. A diver blows a 0.75 liter air bubble. That sounds like V1. The 10 meters underwater doesn't really factor in the problem. It just tells us where he is. As it rises to the surface, the pressure goes from 2.25 atmospheres. Okay, that sounds like P1 to 1.03 atmospheres. That sounds like P2. What will be the volume of the air in the bubble at the surface? Well, from that, okay, I've got P1, P2, and V1. I have 3 of the 4 parts of Boyle's law, right? And the only thing I am missing here is V2. So I would solve this equation for V2, and I would just bring P2 to the bottom of the other side of the equation, and we can just immediately start plugging stuff in. Initial pressure is 2.25 atmospheres. The initial volume is 0.75 liters. Okay, so we're going to multiply those together and divide by final pressure of 1.03 atmospheres. We're going to round our answer to two significant figures because of the 0.75, and I'm going to come up with 1.64, and the unit we're going to have here is liters, okay, because everything else is canceled. 1.64 liters, all right? So very simple, just label the parts in the problem of what you've got, and then see, okay, I've got 3 of the 4 pieces of the law here. This is the one I don't have, solve for it, okay, and plug your numbers in. The second gas law is Charles' law. It's named after a French scientist, Jacques Charles, who lived in the mid-1700s to early 1800s. He is going to notice a relationship between temperature and volume, V and T. He's going to notice that it is directly proportional, which we talked about just a minute ago. Okay, so he observes that as temperature increases, the volume of a gas also increases when the amount of gas and the pressure remain constant. So once again, moles are constant, they haven't changed. This time around, though, pressure is constant. Okay, so we can't change pressure. But V and T do change. So he says that if one goes up, the other one is also going up, which would mean if one of them is going down, the other variable is also going down. Whatever one of them does, the other variable does the same thing. And a consequence of that is the equation looks a little bit different. Instead of being multiplied together, they are divided by each other. So we have V1 divided by T1 equals V2 divided by T2, and that's Charles' law. Okay, so Boyle's law was P1 V1 equals P2 V2. Charles' law is V1 divided by T1 equals V2 divided by T2. Okay, an important thing here, it doesn't necessarily matter which unit you use for volume, but you have to be consistent. However, temperature must be in Kelvin. If you start plugging stuff in Celsius, it's not in the right ratios, okay? Especially if you have a negative value, okay? Because we're not going to end up with negative volumes in this problem. So Charles' law is between volume and temperature. It is directly proportional. Here's the equation. Temperature has to be in Kelvin. Since it is directly proportional, that means as one variable increases, the other variable increases proportionally, right? As one goes up, the other one also goes up. And that makes sense. And what it looks like, okay, so if a inversely proportional relationship is a downward curve that we saw with Boyle's law. Directly proportional relationships are a straight line with a positive slope, okay? Because as x value is getting bigger, the y value is also getting bigger. So directly proportional, you get a straight line. Know the difference between those two. Know which one looks like which one. And notice what happens here. Here's a question. Why does the line stop at 150 Kelvin? Well, what happens if we start cooling down this gas? Eventually, it's going to condense into a liquid. And so what's happening at this particular point is saying that, hey, at 150 Kelvin, this thing is now a liquid. I can't get a pressure anymore or a volume anymore necessarily of that gas. So this dotted line here is sort of extrapolating down to the 0, 0 point, right? It should have a line that goes through the origin. But in this region right here, we can't get any official data because, well, it's a liquid. Okay, so let's try a sample problem here. It says a helium balloon in a closed car occupies a volume of 2.32 liters at 40 degrees Celsius. If the car is parked on a hot day and the temperature rises to 75 degrees Celsius, what is the new volume of the balloon, assuming the pressure remains constant? So just like in the previous problem, let's label what stuff is. Occupies a volume of 2.32 liters. That sounds like V1, 2.32 liters. At 40 degrees Celsius, that sounds like T1. However, we need to immediately just convert that over to Kelvin. That's 313 Kelvin. If the car is parked on a hot day and the temperature rises to 75 degrees Celsius, so let's make that T2, 75 degrees Celsius, which let's go ahead and immediately convert that over to Kelvin, 348 Kelvin. What is V2? Well, so we have V1 over T1 equals V2 over T2. Getting V2 by itself, because that's the only one I don't know, I'm going to bring T2 to the top over here. And I get V2 equals V1 times T2 divided by T1. Okay, so V2 is equal to, well, V1 is 2.32 liters. T2, be careful, make sure you put the right thing in the right spot, 348 Kelvin. all divided by T1, which is 313 Kelvin. We're going to get three significant figures with an answer here. Let's see what we get. 2.32 times 348 divided by 313. Three significant figures, 2.58 liters. Okay, so our next law sometimes goes by two different names. It was discovered by two separate people, Amonton and Gay-Lussac. So you'll hear it called both things. But this law, okay, deals with the two remaining variables that we haven't seen put together, and that's pressure and temperature. So his law states that the pressure of a fixed amount of gas varies directly with the temperature in Kelvin when the volume remains constant. So once again, a fixed amount of gas, that means the moles are constant. We're still not changing the number of moles. And this time, volume is constant as well. Okay, so P and T are the only things changing. Okay, and it's directly proportional, which means, say, as pressure goes up, that means that temperature also has to go up. And the other thing to note is, once again, the temperature is in Kelvin. So it doesn't matter which unit you use for pressure, you just have to be consistent what you put in, what you plug into the equation. But temperature must be in Kelvin. So the law itself looks like, kind of like Charles' law. P1 over T1 equals P2 over T2. Again, directly proportional, just like Charles' law. So you can kind of see how that relationship looks similar and has a similar result where one variable goes up, the other variable goes up, or if one goes down, the other one goes down. P1 over T1 equals P2 over T2. And just like Charles' law, it will result in a line with actually a positive slope, straight line positive slope, going through the origin. Okay, so we got our three laws here, and we're going to see what happens when we take them all together here in a few minutes. But first, let's try a problem. It says the pressure of an oxygen gas inside a canister is 5.00 atmospheres at 22 degrees Celsius. The canister is located at a camp high on Mount Everest. If the temperature there falls to negative 21 degrees Celsius, what is the new pressure inside the canister? Okay, and just like we've done before, it doesn't say use Amonton's law to solve this, but what I would do is sit here and label stuff. Okay, 5.00 atmospheres sounds like P1, 22 degrees Celsius sounds like T1, canister is located at a camp high on Mount Everest, temperature falls to negative 21, that sounds like T2. What is the new pressure? P2. So just from that, I can see that I've got three of the four variables given to me in Amonton's law, and I'm solving for the fourth. So if I didn't know which law to use, label stuff and figure out which law you have three of the four pieces of. Okay, so I've got three of the four pieces of Amonton's law. We're going to solve this for P2. We'll bring T2 up to the top on the other side, and we get P2 equals P1 times T2 divided by T1. Okay, and before we do that, we should probably change these values here into Kelvin. 22 degrees Celsius is 295 Kelvin, and negative 21 degrees Celsius is 252 Kelvin. Okay, so P1 is 5 atmospheres, 5.00 atmospheres. T2 is 252 Kelvin. All that's divided by T1 of 295 Kelvin. And my new pressure, so you get 5 times 252 divided by 295, to three significant figures is 4.27 atmospheres. Something I don't know if I've mentioned yet, but something to be aware of is you can kind of mentally check your answers. You know this is a directly proportional relationship. So if one variable goes up, the other variable goes up. Or if one variable goes down, the other variable goes down. Well, from T1 to T2, we go from 22 degrees Celsius to negative 21 degrees Celsius. Temperature goes down. Pressure should also go down. Well, it started at 5 and ended at 4.27. If you did this problem and you got a number bigger than 5, that means you probably flipped your temperatures right here. Okay, so you can kind of do a mental check to note that, hey, temperature went down, that means pressure needs to go down. My answer better be less than my starting pressure. And that's the case with some of these other problems as well, right? If you know it's directly proportional, you can see what happened to one variable, the other variable should do the same thing. Or if it's Boyle's law, inversely proportional, whatever one of the variables does, the other variable should do the opposite thing. So there's kind of a nice way to mentally check your answers. Okay, and so where does our last law come from? Well, it's going to actually combine the three laws that we've seen so far. So at some point, scientists sat down and realized that when we look at these equations, the variables end up in the same part of the equation no matter which one we're using. For instance, pressure is always part of the numerator, and temperature is always part of the denominator, and volume is also always part of the numerator. And so they said, well, wait a minute, we could actually take these relationships and put them into one equation where we have pressure and volume on the top, pressure and volume on the top, and temperature on the bottom. And so what they did is they actually took all these and rearranged it to say P1 V1 over T1 equals P2 V2 over T2. So you can kind of see how they just combined, they smashed all three of these laws together, and this law is actually called the combined gas law. It's not named after a specific person, it's just combining the three previous laws into what's called the combined gas law. So here, we actually can change, 5 things at once to solve for the 6th thing. All right, we can actually change a lot of variables. We can get actually a solution when we're changing more than one thing at a time here. So that's kind of a neat ability with this equation. So when it comes to combined gas law problems, they're usually easy to recognize because there's a lot of data given to you in the problem. So we'll just read through this one and label stuff. A gas at 110 kilopascals and 30 degrees Celsius fills a flexible container with an initial volume of 2 liters. If the temperature is raised to 80 degrees Celsius and the pressure increases to 440 kilopascals, what is the new volume? So as usual, right, let's pretend we don't know that this is going to be a combined gas law problem. We would need to go through and label everything. So let's go ahead and do that. 110 kilopascals, that sounds like initial pressure. 30 degrees Celsius sounds like T1. With an initial volume of 2 liters, that sounds like V1. Temperature is raised to 80 degrees Celsius, it sounds like T2. And the pressure increases to 440 kilopascals, it sounds like P2. What is the new volume? So you can see here I've got 5 of the 6 pieces of the combined gas law just by labeling things. So let's go ahead and write that out. We have P1 V1 over T1 equals P2 V2 over T2. And we need to solve this for V2, right? So let's go ahead and rearrange this. That means T2 is going to come up to the top, and P2 is going to go to the bottom on the other side of the equation. So we're going to end up with V2 equals P1 V1 T2 divided by, and on the bottom here we will have P2 times T1. Okay? And let's just start plugging stuff in. Initial pressure, 110 kilopascals. Initial volume, 2.00 liters. Final temperature, we need to add 273 to it to turn into Kelvin, so that's 353 Kelvin. The most common mistake here, oftentimes with the combined gas law, is flipping the temperatures, right? That's T2. P2 is 440 kPa, and T1 is 303 Kelvin. So go ahead and do the math on that. 110 times 2 times 353 divided by 440 and also divided by 303. We're going to get 0.583, 3 significant figures, and our unit is going to be liters, right, for volume. And so that about makes sense, right? The pressure has quadrupled. The temperature only changed, 50 degrees Celsius, so it didn't change a whole lot. But the pressure quadrupled, and if you note, the volume almost got cut down by 4, okay, a quarter of what it was originally. So kind of makes sense where that's at. This is just a convenient chart to show you all of the equations put together. Okay, so we got 2 problems for you to try. This first one says a 3.50 liter balloon inside a house at 20 degrees Celsius is taken into a hot car at 65 degrees Celsius. What is the new volume of the balloon? Assume the balloon cannot change pressure. So we'll give you a minute or so here to attempt this one, and then there's one more. Okay, so here's the solution. We went through and labeled everything in the problem. We have V1, T1, and T2, and we turn the temperatures into Kelvin. That means we have 3 of the 4 pieces of Charles' law, right? V1, T1, V1 over T1 equals V2 over T2. We rearranged it for V2, which is what we're solving for. V1 times T2 divided by T1. Plugged in our numbers, rounded our answer to 3 significant figures. We get 4.04 liters. One more for you to try. A gas in a chamber with a piston occupies a volume of 0.500 liters at 1.25 atmospheres. What is the pressure if the piston is compressed and reduces the volume to 1.100 liter? Assume constant temperature. So go through and label things if you're not sure, and then figure out which law that you will use to solve this. Okay, so after labeling things, we have V1, P1, and V2. We plug everything into the equation of, well, we got 3 of the 4 pieces of Boyle's law. So P1, V1 equals P2, V2. Solve that for P2, since that's what we're asked to solve for. P1 times V1 over V2. Plug in our values. Our answer has 3 significant figures. We should get 6.25 atmospheres. Hopefully you did okay with those. Now it's time to try some on your homework.